You're watching a Channel 98 NBISD TV production.
Oh, 100.3, my. Hi there, welcome to Deja Vu, it's Algebra 2. As always, I'm your host, Kevin Corpy. But unlike always, I'm a little blue today. It's not just because I'm wearing a blue shirt. See, I think I got a fever. The thermometer tells me so. 100.3 degrees. How I know that that's actually my temperature? In other words, how accurate is this thermometer? Is there a certain error that is built into this? Might I actually be 100 degrees or 101 degrees? It's kind of important to know, right? Especially if I want to call in sick to school. It's got to be over a certain degree. Well, the whole point is to feel better. And I think I have the cure for my fever today. It's math. We're going to talk about absolute value functions today on episode 5. And it always helps me feel better. I hope it'll make you feel better. Why don't you download those worksheets from the district website, www.newbraunfels.txed.not, and let's explore some math together, and hopefully we can all come out on the other side feeling much, much better. All right, lesson 5 already. Absolute value equations, inequalities, and functions. Well, absolute value equations and inequalities can be used to represent acceptable ranges of a product or margins of error. So if something's coming off an assembly line, they have an idea as to what the quality needs to be, but they might be willing to accept some deviation from their standard only within a certain range or within a certain tolerance. That's what an absolute value function will take care of. Now, to understand how to work with them, we first need to look at two types of compound statements that involve inequalities. The first one is called a disjunction. Now, a disjunction is a compound statement that uses the word or. Disjunction uses the word or, and it's an inequality with two disjoint or unconnected intervals. Down here we have a graph of a disjoint interval. This is a number line graph. We have an open circle over here at -6, which means we're not including that value. And then we have the shaded region that is to the left of -6. We have a solid dot on -1, and then we have a line that goes to the right. And so this is an inequality represented on a graph. And we can write a compound statement to represent this graph. So we're looking for the solutions, and we want to write the solution set. So I can write it as the set of all x's such that, that's the preface or the prefix for set builder notation, such that x is, well, we have to be left of -6, so that's strictly less than -6, not less than or equal to because it's an open circle, or we can say our x values, our solutions, have to be greater than or equal to, because it's a solid dot, that x value of -1. So the word or is a disjunction because these intervals are disjoint, meaning it is impossible for our solution to be both less than -6 and greater than -1 at the same time. It's either in here or it is in here. It's a disconnected interval. Now there's a couple of other symbols we can use for this word or. We can actually use something called the union symbol, and we can write it like this. The union symbol is like a capital U without the kickstand, and we use that to join together sets of information. But it's just a mathematical symbol meaning the word or, and we can also write this in interval notation. Remember, interval notation always lists an endpoint from left to right. And we use parentheses for the strict inequalities and brackets for the less than or equal to. So if we're going less than -6, we're going to have to start at -infinity. In other words, these points will go on forever. And -infinity or positive infinity always get a parenthesis, comma, our endpoint is -6. Now because it's an open circle, we can't include it. We put another open parenthesis. And then we use the union symbol to join the sets together. And then we're picking up at -1, and we can include it so it gets a bracket. And then we cruise all the way to the right for how far? Well, it goes on indefinitely, so comma, infinity. So these are listing the x values, even though we don't have the x value here. And again, we're assuming that we're talking about all real numbers if we don't specify what type of set of numbers. So that's a disjunction. It's an or disconnected interval. The next type is a conjunction. A conjunction is a compound statement that uses the word and. A-N-D. It's an inequality with two, not disjoint, but two connected intervals. So let's look at this little number line down here. I have a number line, and I got two circles, and it's a little hard to see, but I got an open circle around 4 and a shaded region between 4 and 5 with another open circle on 5. Now notice that if I'm trying to write an inequality for this solution set, every value of x that's in this shaded region is both greater than 4 and less than 5 at the same time. It's not one or the other. So this is an AND case. And we can write this as a compound inequality that looks like this. Again, the set of all x's such that we can do this two ways. We could say x is greater than 4, and we can actually write the word and. X is less than 5, and again, it's a strict inequality because it's not equal to. We can use another symbol here, similar to the union symbol, called the intersection symbol. And the intersection is a mathematical symbol for the word and it's kind of like an upside down U. And that means and, or intersected with, x is less than 5. But because this is a connected interval, we can actually write this as a compound inequality without the word and in it, and it would look like this. The set of all x's such that, here's an easy way to set it up. If it's a connected interval, our solutions are between 4 and 5. So we can write down 4 and 5 and put our x's physically in between them. And if we write that now with less than symbols on both of them, we get a single compound inequality. And the way we read this is x is greater than 4 and x is less than 5. So the less than case is going to end up being the and case. And this is actually a preferable method right here. If you wanted to write it in interval notation, you would need 4 and 5 as your endpoints. And because you're not including either one of them, they would both get parentheses. So all of these are equivalent notations to the solution set to this little shaded region. Now you do have to be careful. On that right here, from 4 to 5, that is an interval. But if you're not aware of the context of what we're talking about, from x equals 4 to x equals 5, you might stumble across that and think it's an ordered pair. In other words, an x and a y coordinate. So it's very important, especially when you're talking about interval notation, that are open intervals on both sides, to understand you're talking about an interval of x values and not an ordered pair of x and y values on the coordinate plane. Okay, let's try to solve some of these dudes. Here's the first example. We want to solve each of the inequalities, and then we want to sketch a linear graph that shows the solutions. So we're kind of going backwards here. Well, this is an OR case, I could tell, because it has the word OR, and I want to solve these algebraically. So our goal is to isolate x, just like we did with an equation. I'm going to work these as two separate equations. So over here, if I add 5 to both sides, the inequality is less than. This becomes a positive 5 minus 2 is 3. So I get x is less than 3, and that side is done. Over here, I have to divide by a negative 2. Now I'm going to show this step because there's one important thing to remember when you're dealing with inequalities, and that is when you multiply or divide by a negative number, you must flip the inequality because you're jumping across the number line from positive land to negative land. The inequality is going to flip, and I see a lot of students miss that. So I get x, and then I get 5, and since it was less than or equal to now, it flips to greater than or equal to. Now this is an OR case. If you want to graph this, you'll help see why it is a disjoint or a disjunction. Here's my number line. Here's 0, so 1, 2, 3 is there. 4, 5 is there on the number line. I need to be strictly less than 3, so I'm going to put an open circle around 3. And you can also draw, instead of shading on the number line, it's appropriate to put an arrow coming up and showing the direction. Sometimes it gets hard to shade on top of a line that's already there. Greater than or equal to 5, I'd put a solid dot on 5, and it has to be greater than 5. So I come up and to the right. Now notice you can clearly see that this is a disjoint or a disjunction. The values are going away from each other. You can't be less than 3 and greater than 5 at the same time. It's one or the other. So the greater than case is going to end up being the OR case, the disjunction. Here's another one. 1/2 c is greater than or equal to 2 and. All right. So this is a conjunction. It's got the word and. Let's go ahead and solve. I've got to multiply both sides by 2, and I get c is greater than or equal to Negative 2 times 2 is negative 4. Now I don't need to flip the inequality here because I multiplied by positive 2, not negative 2. And on this one I have to do two steps. I subtract 1. I get 2c is less than 1 minus 1 is 0. And if I divide by 2, c is less than 0 divided by 2, which is 0. So let's go ahead and draw the picture. The picture is going to look like this. Here's 0. And 1, 2, 3, 4. There's negative 4. So if I sketch the graph, if I'm not sure if it's an and or an or, even though it says it here, I have to be less than 0. So I'm going to draw an open circle, come up and go this way. And then I have to be greater than or equal to 4. So solid dot on negative 4, and greater than is to the right. Well, these things are going to intersect. And remember this symbol for intersection right there. That's the and case, when your intervals overlap or intersect. So you can write the solution set for this one as the set of all c's such that we're between negative 4 and 0. So again, negative 4, 0. Put our variable c there. And now I got to be careful because this gets a less than or equal to because it's solid. And here I get a strict less than. So that's writing it in set builder notation. So we got the or, the disjunction, and the and, the conjunction. So what is the absolute value anyway? Well, the absolute value of a number, call it x, denoted like this. It's basically two vertical bars with the x in between there. That's the symbol for the absolute value. It's defined to be the distance from x, our solutions, to the number 0 on the number line. Okay, so it's a distance from 0 to a number on the number line. And because we're interested in distance and not necessarily the direction or the directed distance, we're always looking at positive values or maybe 0. So we say non-negative values. 0 at the very least or positive numbers. So we can't have negative numbers when we're talking about absolute values. It's a distance, positive distance. Now here's the precise mathematical definition. We can write it as what's called a piecewise function. That's what this is, a piecewise function. And what it does is it allows us to consider the two cases, when x is positive or 0, non-negative, or when x happens to be negative, less than 0. Well, if x is positive, greater than 0, or 0, I don't need to do anything to what's inside the absolute values. I take it as is. So it's just x when x is greater than or equal to 0. However, if x is less than 0, like negative 5, here's an example, the absolute value of negative 5. How do I make negative 5 positive? Well, I have to take the opposite of it, or I need to multiply that number there by a negative 1. So I'd get negative negative 5, which is in fact 5. And that's what this says. It says when x is less than 0 or negative, I have to take x and multiply it by negative 1, like I did down here, to get a positive number. This can kind of throw some people off because they're staring at this and they see a negative, and they know absolute value can't be negative. But remember, in this case, x itself is negative. So the negative in front makes it positive. You'll get the hang of it after you work enough. All right, now, the absolute value equations and inequalities can be represented by compound statements. And we're going to look at disjunctions and conjunctions and actually an equation right here. So let's look at this number line. We've got the absolute value of x equals 4. So what does that mean? We're looking for all the values of x that are 4 units from 0. Well, here's 0 on the number line, so 4 units away in either direction. So 1, 2, 3, 4. There it is. It's a solid dot, so that this is 4 units. And then 1, 2, 3, 4 in the other direction would be 4 units. And because that's an equal sign and not an inequality, I just have my two solutions. In other words, 4 and negative 4 are the values that are 2 units away. So I could write the solution set as the set of all x's such that x equals negative 4 or union x equals 4. Okay, so that's what we can do with an equation. One's positive, one's negative. If I have this inequality that's less than, the less than case, well, that means that I'm looking for all the values of x that are less than 4 units or within 4 units of 0. Well, here's 0. All these values up to 4 and including 4, I better make that less than or equal to, and all these values to the left of 0 up to negative 4 are within 4 units of 0. Some are 1 unit away, some are half a unit away, but they're all within 4 units. So this is the connected case. So this would write as our compound inequality with our values of x being between 4 and negative 4. So the less than case goes to a less than over here, and this is the and case. So less than and go together. And I'm going to get to that here more in just a minute. And the last one is the disjunction x, the absolute value of x is greater than 4. Well, this means that we have to be at least 4 units away from 0. So I can't include anything within 4 units. We have to start at 4, and again, this should be greater than or equal to. 4 units would work, and anything beyond 4 is greater than 4. And over here on the other side, there's negative 4. It's 4 units away. Anything to its left is beyond 4 units away from our center of 0. So notice that these two intervals go away from each other. They're not connected. They are disjoint. So we would write this solution like this. The set of all x is such that x is less than or equal to negative 4, or x is greater than or equal to 4. So whenever we have a disjoint interval, we want to use the word or we can use the union symbol. But what we want to do is reserve this compound inequality up here for the AND case, where we use less thans in the compound inequality. It's preferable to use the or for the disjoint interval. We can summarize now. If we summarize right here, this is going to be something that's worth memorizing. Okay? So if I have the absolute value of x equals a, I can break it down to my two solutions, which is going to be x equals the opposite of a or positive a. And that was like our 4 and negative 4, and that's really just the two cases from our piecewise function. If I have the absolute value of x is less than a, that's going to be the AND case. The less than is the AND case. Well, all you do is you basically drop the absolute values for one of them, and to get the other solution, you flip the inequality, make a less than greater than, and change the sign of a. Okay? And that's the AND case, so we can also write that like this, the compound inequality. And the last one is the greater than, and this is the OR case. And we do the same thing. We drop the absolute values to get one of our equations or inequalities, and then we flip the inequality from greater than to less than and change the sign. And it's because of the definition. If you want to see why here, we get x is greater than a if a is positive, but if x is negative, we have to take the opposite of it. And then if I solve this by dividing through by negative, that's how we get our other solution. So each of these are going to generate two inequalities or two equations. All right, now here's the way to remember it. Less than, you can write it less than, and that helps me remember it, less than. And the other one is greater, which I write as great or, with a capital or, than. And it's kind of cheesy, it's kind of a gimmick, but it works. Less than is the AND case, it's the connected conjunction. Greater than is the disjunction, the OR case. Just like I thought, my temperature's coming down. I'm feeling better, can you tell? Why don't you take a quick break and come right back and join me? But while you're gone, ponder this. What did one math textbook say to the other math textbook?
Yesterday, my friends told me to smoke some weed, and I did. Then today, they said I should try to outrun Tick-Tick, the little lumberyard dog. And I don't think I can. I'm an idiot. I'm doing stupid stuff, and that ain't me.
No! Live above the influence. Above them, above weed.
Horseradish. Is that for horses? Remember me, Mr. Lobster? From last Tuesday? Banana. 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 Here comes the rain. We need a hat. And why do we need a hat? That's right.
When you talk with your child, you build vocabulary, and learning starts long before school does. For more tips, go to bornlearning.org.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, and I'm very healthy. I'm feeling much, much better, thanks to the math. Did you think about the answer to the question? What did one math textbook say to the other? It said, leave me alone. I've got my own problems. Yeah. Let's get back to some more math problems of our own. All right, let's put those three different scenarios into practice and actually solve some inequalities involving the absolute value. So here we go. We want to solve for x. Remember, solving for x is going to require us to find the values of x that make this true. Well, this is an equation sign. So based on the definition of the absolute value, I can break that into two cases. X minus 7 equals 5. And I just take the x minus 7 when it's positive. And I can get the other case. It's going to be x minus 7 equals negative 5. And that's based on this little scenario up here. Whatever's in the absolute values, you set it equal to a or equal to negative a. In this case, 5 or negative 5. Well, now I have two equations, so I could solve. If I add 7 to both sides in this case, I get x equals 7 plus 5, which is 12. And if I add 7 to both sides in this case, I get 7 minus 5, which is 2. And so my two solutions are the set of all x such that x is equal to 2, comma, 12. There's only two solutions. Now, notice that these are not symmetrically on either side of 0 like we saw previously. And that's because if you have something written in this format, x minus 7, you can think of it as x minus c, where c is your new center. So we can read this as the distance from x to the new center, 7, has to be 5 units. So if you draw a little graph of this, here is 7. If I went 5 units, 1, 2, 3, 4, 5, that's 7 plus 5. That gets me to 12. Or 7, 1, 2, 3, 4, 5, that's minus 5. That puts me over here at 2. And so those are the two values that are 5 units away from my new center, c, of 7. So just another way to look at it. Here's one that's a less than or equal to. So remember, the less than case is the and case. This is going to be a connected interval. The first thing I'm going to do is get rid of this 3. I'll multiply both sides by 3, and I get less than or equal to 3. And now I will break up my absolute value. It's the less than case. So in one case, we just drop the absolute values. And in the other case, we flip the inequality, so it becomes greater than or equal to, and we change the sign on the other side. And that's going to be consistent for the two inequalities. Drop the absolute values, take it as is, then flip the inequality and make it negative. And you'll see then, if you memorize that, this will come out to be the and case. If I add 7 to both sides, I get less than or equal to 10. Divide by 2, and I get 5. So x is less than or equal to 5. And over here, I get 2x is greater than or equal to 7 minus 3 is 4. Dividing by 2, x is greater than or equal to 2. So, greater than 2 and less than 5 at the same time? Yeah, that'll happen. So how do we write our solution set? It's the and case. It's set of all x's such that x is between 2 and 5. So there's 2, there's 5. You've got to write them in increasing order. 2 is on the left of 5. And if you do that, then you can just stick your less than or equal to's, your inequalities in there. And that is the and case. That's the conjunction. All right, so remember, to sum up here, a disjunction is going to be something like the equation where there's two separate points that are disconnected, or the greater than case where they are actually disjoint intervals. So greater than or equal to is the greater. And then I've got the conjunction case, which is the less than or equal to, less than case. That'll help you remember it. Okay, now what we want to do is look at the absolute value function on the coordinate plane with the x and the y-axis. So if I just set my absolute value equal to f of x, I can actually sketch it by looking at a table of values. And it's kind of given away over here, so pretend you don't see that. Back in Algebra 1, when you were first graphing functions, you made a table of values. X is your independent variable, and our function are the dependent variables. So I just chose a nice little sampling of x values, -3, -2, -1, 0, 1, 2, 3, some nice integers. If I plug those into the absolute value, I'm going to get the absolute value of -3 is 3. The absolute value of -2 is 2. The absolute value of -1 is 1. And that's because -3, -2, and -1 are all 3, 2, and 1 units away, respectively, from 0. The absolute value of 0, well, that's 0. It is at 0, so there's no distance. 1 is 1 unit away from 0, 2 is 2 units away from 0, and 3 is 3 units away from 0. So again, the absolute value by process, we're just making everything positive. But again, it's the distance from 0. Well, if I translate these distances now onto the y-axis, I get a graph that looks like this. And you could plot the points. -1, -2, -3. 3 would be right here. -2, 2 would be right here. -1, 1 would be there. 0, 0, 1, 1, 2, 2, 3, 3. And then you could connect the dots. So your absolute value graph is the one that looks like the V for victory graph. Okay? What it is, it's basically a function composed of two linear pieces. We've got a line to the left of 0 that has a slope of -1. It's your 45-degree decreasing line. And then there's a sharp turn right here at the origin. And then we have the line that's also 45 degrees, but it's the increasing line with the slope of +1. Okay, so that's the absolute value function. You'll come across that quite a bit more later this year. And if you go on to take pre-calculus or calculus later on, it shows up quite a bit. All right, now it's time for
Deja Review.
Okay, so here's a nice application of absolute value inequalities. It's useful for expressing, again, acceptable intervals of value such as margins of error, standard deviations, or tolerances. A thermometer. Well, A thermometer is useful for measuring your temperature, as you already know. Let's say we have a thermometer here, and we measure 5 different readings from somebody, and we realize then that the thermometer is actually accurate to within plus or minus. That plus or minus is important. 15 hundredths, or 0.15 degree Fahrenheit. Which of the following represents the actual temperature T of a person if the thermometer is reading their temperature at 98.5 degrees Fahrenheit? So what this is, 0.0 or 0.15 is the error. It could be positive, which means this number could be that much more greater than this, or it could be negative. It could be 0.15 less than this. So the actual temperatures that our body can actually be are going to be 98.5 minus 0.15, and the other one would be 98.5 plus the margin of error, 0.15. And so what does this give us? If we subtract, we get 98.35 degrees Fahrenheit. Oops, over here. And if I add 0.15, I get 98.65 degrees Fahrenheit. So assuming that this thermometer is accurate to within 15 hundredths of a degree, getting a reading of 98.5 means that my temperature actually might be anywhere in between these two intervals. This would be a connected interval. So that's going to translate back into the less than or equal to case. So if we look at our choices, we got less than or equal to, less than or equal to, greater than, greater than. It can't be either one of these. Our temperature can be anywhere within that, so it's got to be one of these two. The only difference is the minus and the plus. Well, remember, if we remember this format, x minus c, where c is our center, then this one right here, A, would tell us that our temperature is going to be within less than or equal to 0.15 degrees of our center, which is the actual reading of 98.5. And so the answer is A. So we can represent a compound inequality as a single absolute value inequality. All right, so a big show today dealing with one function, the absolute value function. One small function, but many, many applications. We're going to be using it to figure out what tolerances, margin of errors are, ranges of acceptability. And it's important when you're dealing with thermometers because you have a whole range of values that your temperature actually might be instead of one specific value. I hope you had a good time on today's show. I hope you feel better like I do. Until next time, I'm Kevin Corpy reminding you to do your homework.